When faced with a complex function whose limit is difficult to evaluate directly, especially when it involves oscillation like trigonometric functions or undefined forms, the squeeze theorem, also called the sandwich theorem, is an invaluable tool. It allows us to find the limit of a function by squeezing it between two simpler functions that share the same limit at a point. The theorem states, suppose that for all x in an open interval containing c, except possibly at x equals c itself, the following inequalities hold. G of x is less than or equal to f of x, which is less than or equal to h of x. If the limits of g of x and h of x as x approaches c both exist and are equal to the same value L, then the limit of f of x as x approaches c must also be L. Why it works? Imagine g of x and h of x as two slices of bread. The function f of x is the filling, always lying between them. As x gets closer to c, both slices of bread, g of x and h of x, approach the same height L. The filling f of x trapped between them has no choice but to approach L as well. Applying the theorem involves key steps. First, identify the squeezed function. Recognize the function f of x whose limit is tricky to find directly. Second, find bounding functions. Construct two functions, g of x and h of x, that satisfy g of x is less than or equal to f of x is less than or equal to h of x near c. These should be simpler functions whose limits at c are easier to compute. Third, evaluate bounding limits. Show that the limit of g of x as x approaches c equals the limit of h of x as x approaches c, both equal to L. Fourth, conclude, by the squeeze theorem, the limit of f of x as x approaches c equals L. Classic example, find the limit as x approaches 0 of x squared times sine of 1 over x. The function sine of 1 over x oscillates wildly between -1 and 1 as x approaches 0. Direct substitution fails and limit laws don't apply easily. Use the bounds of sine. -1 is less than or equal to sine of 1 over x, which is less than or equal to 1 for all x not equal to 0. Multiply all parts by x squared, noting x squared is greater than or equal to 0. Negative x squared is less than or equal to x squared times sine of 1 over x, which is less than or equal to x squared. Identify g of x equals negative x squared, f of x equals x squared times sine of 1 over x, h of x equals x squared. Evaluate the limits of the bounds. The limit as x approaches 0 of negative x squared equals 0, and the limit as x approaches 0 of x squared equals 0. Since g of x is less than or equal to f of x is less than or equal to h of x and both bounding limits equal 0. The squeeze theorem gives the limit as x approaches 0 of x squared times sine of 1 over x equals 0. The squeeze theorem is particularly powerful for limits involving trigonometric functions multiplied by expressions going to 0, like the example above, functions defined by oscillation or bounded behavior, and establishing fundamental limits, such as the limit as x approaches 0 of sine x over x equals 1. This video is part of our free calculus course for engineering students with over 100 subtopics to explore. Find the link in the description.